Swayam Prabha. Digital India. Educated India.
Welcome to next lecture on decision analysis as part of this course on infrastructure systems, decision risk and resilience. In this particular lecture, we will do some quick refresher on a decision problem that I introduced in one of the earlier lectures to get students and audience oriented towards what it entails in a typical decision problem. And then we will start constructing our own decision trees using classical as well as Bayesian approaches. So here is that example that we already discussed regarding a decision problem where there are two alternative designs that are being considered for a structural scheme of the building. Design A is based on a conventional procedure, how things are usually done, and its probability of satisfactory performance is 99%, and there are 1% chances of its failure or non-satisfactory performance, and it will cost something around $1.5 million. Similarly, design B is based on modern concepts and will reduce the cost of building to $1 million. Of course, there is a substantial saving of almost $500,000. So we should be inclined to go with design B and case is solved. But that's where additional information comes into picture. That is, concept of reliability comes into picture. Now, further information is given that reliability of design B is not known because it's a new design. People cannot comment on its reliability or long-term performances. But structural engineers made some estimates that while designing, we made some assumptions. If these assumptions are right, then structure B would also have the reliability of 99%, same as structure A. However, if assumptions are not valid, in that case, reliability is only 90%. According to the judgment, there are only 50% chances that their assumptions are valid. So they made certain assumptions. They are 50% sure that those particular assumptions are right. If assumptions are indeed right, then structure is 99% reliable. If assumptions go wrong, the chances of failure increases to 90% in comparison to 99% for the option A. Now, if there is an unsatisfactory performance, there is going to be the cost. There may be a structural collapse. You may have to pay for the insurance. There may be damages to life and property, and hence damages always have a bigger costs associated with it, sometimes more than the design costs itself. And that is where decision making becomes essential, very critical. That is, cost of infrastructure itself may be less, but if infrastructure does not perform to intended level of functionality, it may in fact exacerbate the secondary damages that may get inflicted on the society or community where it has been placed. And in this case, the cost is around $10 million, around 10 times of the cost of construction. Now there is a dilemma. Should we go for option A or should we go for option B? Before we solve that, let us pay attention to various components that we saw in this particular problem. We saw that there are multiple elements of uncertainty. multiple costs are associated, and we have to integrate all of these together. And this is not the mathematical integration, but to bring all these information together and put it into a systematic framework. And that is where decision trees become important. What we saw earlier is a decision problem. So all the components of decision problem can now be integrated into decision tree. What decision tree will have? It will have all feasible alternatives that are available to us. In this case, two designs are our feasible alternatives, design A and design B. It will also list all the probability assignments. That is, what are the chances of satisfactory performance of A, B, C, D if we have multiple options available. In earlier case, we only had two options. So what are the probabilities associated with A and B? And monetary consequences or utility consequences associated with each outcome. For example, if structure is performing satisfactorily, the only cost we are going to bear is the construction cost and maintenance cost. If structure fails after construction, we have already paid for construction cost, and now we have to pay for the consequential costs, which are 10 times the construction cost. So that all information can now be systematically integrated into the decision tree. How to construct a decision tree? It can be a diagrammatic representation of that big text that we saw. It will have a few nodes and links or edges between those particular nodes. Every decision tree starts from a square node. Square would be drawn like this, of course, and we will call this square node as the decision node. That there are two alternatives available. So the first split happens at the square node. After square node, we encounter a circular node, and we call this circular node as a chance node. And chance node will have probabilities associated with it. And finally, we will have terminals, which typically end up with costs or utilities. We will talk about utilities in subsequent sections, but right now we will use the word costs and utilities interchangeably. That is, what is the cost of going with option A and option B. And when all these elements, that is alternatives, probabilities and costs, are listed exhaustively, we end up with a decision tree that can help us make decision in a much informed manner. I will put all these things together in a generic way, that this is how a typical decision tree with multiple options look like. This is the first square node that we spoke about. A1, A2, A3, all are the alternatives available with us. A1s and A2s will have certain probabilities. For example, in earlier case, theta 1 can take value of 0.99 and theta 2 can take value of 0.01, where theta 1 is associated with satisfactory performance, theta 2 is associated with non-satisfactory performance, and U1 and U2 are the costs associated with theta 1 and theta 2. Now, if you pay attention to this, we have been talking in terms of conditionals here. Given that we go for A1, what is probability of things going right? Given that we go with A1, what is the probability of things going wrong? And this cost is function of decision we made and the values of probabilities associated. So here A1 theta 1, A1 theta 2 comes into picture. Now, if I have n number of alternates available, I can repeat the same pattern. But if you notice that when I talk about walking along A2, I will again encounter theta 1 and theta 2 at my chance node, which is represented in circular fashion. Now, theta 1 would be conditional on that I have chosen decision A2. Theta 2 will also be conditional that I have chosen the decision A2. And the final costs would be function of A2 and theta 1. A2 and theta 2. And depending upon more details available, these decision trees branches can take much more complex form. We'll not worry about it at this stage, but all these components when put together gives us a decision tree to systematically analyze and take a call on the options available. There are few points that we have to note before we start constructing our own decision tree. Outcomes from chance node are mutually exclusive and collectively exhaustive. What does these two words mean? Let us pay attention to that. Mutually exclusive means that either structure is failing or structure is not failing. Theta 1 and theta 2 are mutually exclusive of each other. They are collectively exhaustive. That is, sum of probabilities at each chance node should be equal to 1. Probability of success is 0.99. Probability of failure should be 1 minus probability of success, that is 0.01. And that has to be followed at each chance node to have a complete decision tree. And that takes care of mutual exclusivity and exhaustivity. Sum of probabilities at each chance node should be equal to 1. If we are ensuring that our entire space is captured, we have already addressed this part while talking about collective exhaustive, the probability should sum to 1. Only then we will say that the description of each chance node is complete. And finally, the desirability of consequences of each outcome is measured by the utility value recorded at end of the sequence. At the end, we will convert it either to a dollar value or rupee value or some utility, and we will compare across that so that which particular alternative gives us the highest utility, even in terms of money or otherwise, and that is going to be our final decision. Now, a lot of argument can be placed here that is money a right measure to take a decision? Of course not. Certain things cannot be monetized. For example, life cannot be assigned a dollar value. But we have to start from somewhere, and then with this particular backdrop, various socio-economic factors can be further included into these particular decision trees. These are good starting point, but not the end point of the analysis, but they give us some systematic quantification of whatever decision we are going to make, on which other elements around the social discussions can be added to that. So with that, we can go back to our problem again and try to come up with our decision problem. Same problem stated again, but now once we will make decision tree of it, it would look a very different and beautiful problem. Same text, two options A, B having different probabilities. So we have to construct the decision tree for this. So let us start this process of constructing our own decision tree. What is the first step? We have to place a square node from where alternatives will be born. I also call this as a root of any decision tree. From these particular root, two branches will take off. One is associated with option A and other is associated with option B. Now, option A is not guaranteed to perform satisfactorily 100% time. In fact, it is stated that it will perform to desired level of functionality 0.99% times. So we will say that chance of not failing. Anything with the hat makes it not failing. Chance of failing should be 0.01, and this takes care of mutual exhaustive as well as exclusive events happening here. Now, when A does not fail, what is the cost associated with that? Cost associated with that is whatever is the cost of construction, 1.5 million, because if you are going with A, you have to construct A. So the cost is 1.5. If A fails, what are the costs associated? 1.5, the cost that we incurred while constructing it, plus the additional costs or the consequential costs we have to pay when the structure or infrastructure fail, which is another 10 million. So the total cost becomes 11.5. In this case, it is 1.5. Now let us do the same exercise for option B. When we talk about B, this particular decision tree will take more interesting form because we don't have confidence on being failing or not failing. We have made some assumptions. If assumptions are correct, chances of it happening is 50%. Or assumptions themselves can be incorrect. Chances of it happening again is 50%. So again, this is a chance node. Now, when assumptions are correct, what is the chance of not failing? F naught is equal to 0.99. When assumptions are correct, still our system can fail, but with a lesser probability of 0.01. When we go here, again we end up with these two branches, that if my, I think I sort of, good thing is that the probabilities are same. So first I wrote when infrastructure does not fail or assumptions are correct. Second one is when assumptions are not correct. C naught is equal to 0.5. In that case, probability of failure would be a bit higher because I made my model based on some assumptions. Those assumptions have gone wrong. So there is more chance of system being failing, which is 90%. And system not failing 90% and system failing, of course, is 10%. Again, 0.9 plus 0.1 takes care of the entire space fully. What is the cost associated? So when it does not fail, cost is 1 unit, 1 million for construction, because B is cheaper to go with. If it fails, cost is 10 plus 1. 10 is the failure cost, a consequential cost, and 1 is the construction cost. Similarly, if it does not fail here, the cost here is the construction cost, and cost here is 10 plus 1. So this entire problem that we listed in verbatim is now expressed as a decision tree, where everything on top, that I am now highlighting in purple, it represents the elements associated with option A, and all the elements that I am highlighting in green are the options or the partitions that are associated with the outcome B. I can do the weighted summation of everything for A separately. I can do weighted summation of everything for B separately. Whatever gives me more benefit, that should be my decision. So how to calculate this into decision? Let us look into picture. Given that I go with option A, what is the expected costs associated with A? If it does not fail, 99% chance, cost associated is 1.5, or it fails 0.90, and 1 minus 0.99, sorry, not 0.90, it is 1 minus 0.99, because if it does not fail, chances are 99%. Chances of failure would be 0.01 multiplied by total cost, which is 11.5. So what we did, 0.99 multiplied by the cost written in front of it, and when it failed, 0.01, and the costs associated with this particular branch, which is 1.5 plus 10, 11.5. Similarly, when I go for B, expected costs, when I go with option B, here there are 50% chance that my assumptions are correct. When my assumptions are correct, chances of not failing is 0.99. Associated costs that time is 1 unit. Chances of it failing is 0.01. Associated costs are 10 plus 1. And when my assumptions are incorrect, that can happen with 50% chance. That's why 0.5 comes here. It being failing is 0.90. It being not failing is 0.90. Costs associated is 1 unit. It being failing is 10% or 0.10. and costs associated is 11. See here it is 11. Previously it was 11.5 because it is conditional that we have gone with option B. So once we have conditioned the costs on B, no element of A will come here. When it was conditional that we have gone with an option A, no element of B would come here. Hence the costs are essentially separated for component A and B and summed differently for individual branches of the decision tree that we have constructed. When we simplify it, this number comes out to be 1.6. For B comes out to be 1.55. That is, if we go with option A, the expected costs are $1.6 million. If we go with option B, the associated costs are $1.55 million. And despite all the confusion, uncertainties, option given, I have come up with one finite number that the cost associated with branch B is lower than A, and hence with given option, I should go with the option B or design B with a justification or a mathematical rationale to do so. And this is what decision tree and decision making looks like despite all the confusions, options and uncertainty that is available to us. Of course, this is a very, very simple example, but we also encounter decision tree in real life. The previous example that I took is one of the examples in the textbook that we are following, that is Ang and Tang volume 2. But the example that I am talking about is a real world example from one of our own projects that we did for one of the stakeholders. And this is an interesting problem. What it states that there is a subway road, that road that goes under a railway bridge in vicinity of a large reservoir. That reservoir is full most of the times. When that subway was being constructed, the designers missed accounting for the groundwater flows that may come from the reservoir. While water from rains and other sources were accounted for, that reservoir in proximity, we missed somehow. Hence, it was proposed that we should do some retrofitting and avoid the flooding situations in the subway. So a consultant is hired to model subsurface flows and design appropriate remedial measures for that particular infrastructure. The subsurface flow model predicted that groundwater seepage is 100 gallons per minute with 90% probability and 120 gallons per minute with 10% probability, because modelers would also not have all the information that they would desire available to them. So they will also make some approximations about subsurface strata, about level of water in the reservoir, how far that particular water is, when you also account for the porosity of the soil, how much length that water has to travel to reach the subway and so on. So that would give us different ensembles of outcomes. In this case, 100 GPM with 90% probability and bit higher flow with a bit lesser probability, that is with 10% probability of 120 GPMs. Also, two pumps are available. One's cost is 17 units. I'm not worried about dollars or $1 million or $1,000, but it's all relative exercise. So we need not carry the 10 to the power 5s and 6s with us. And the cost of pump A is 20 units to pump out discharges back to the reservoir. Of course, a smaller pump will also cost less money. Larger pump will cost us more money. If flow is less and larger pump is installed, we might have wasted some money, but the cost of maintenance of larger pump in that particular case would be a bit lesser because its capacity is much more. It is running at lesser load. So the deterioration would happen at bit slower rate, and all that numbers are also needed. Now, since pump B is of smaller capacity and discharge is indeed higher, that means there may be a situation of flooding. So what we may have to do is that if we end up installing a smaller pump and more water comes in, we may have to augment the capacity and install another smaller pump, which may cost another 8 units. The design life of this entire project is 30 years. and during that time we are going to encounter certain maintenance costs, replacement costs, that we calculated to net present value of 22, 21 and 5 units. There is a new term that I have introduced, net present worth or net present value. When we will talk about money matters in decision making, we will talk about this net present worth, but right now these are the costs that we may have to pay uh, lump summed at today or at the decision making point for various pumps. For A we may have to pay 22, for B 21, and for C we may have to pay 5 units. If the discharge is indeed 100 gallons per minute, pump A is installed, the operation and maintenance cost of pump A can be discounted by 2 units. Discharge was less, you installed a bigger pump A, so the deterioration would be at much slower pace, so you will save some maintenance costs there. However, if discharge is 100, pump capacity is also catering to same discharge, there may be heating problems and you may have to change the coils frequently, so the cost cannot be discounted in that particular case. Also, a third option is available, that let's not worry about installation of any pumps and install a permanent cut-off wall beneath the surface like bentonite slurry seal that would cut off all the phreatic lines and water can never enter into the subway, because you have provided some insulation to that particular water coming into subway, and that of course will cost a lot of money. It would cost us 41 units. Now question is simple, draw the decision tree and find the best possible alternative. Too many components, easy to get confused, so even if I have to do it now as a practitioner, the first thing I will do is diagrammatically represent all the elements around involved in this particular question and understand what is given and what is being asked to us. So here is a representation of the same problem. Here is a reservoir. Here is that particular subway. That is our element of interest. Railway is positioned on top of it, and this is being used by vehicles most of the times. Two possible flood levels are there, 120 GPM. This can happen with 90% chance, and 100 GPM. 120 GPM higher flow happens with 10% chance, and 100 GPM happening 90%. Higher has less probability, lower has more probability. Let us keep it simple with so many numbers involved. Two options are available. Either we install type A pump, which is of capacity 20 units, or we install type B pump, which is of capacity 17 units. Since this is a smaller pump, this may also need type C pump if our assumption here goes toward that 10%, and that would cost some another money, another 8 units to take care of that mismatch in capacities. Third option is put a bentonite seal for a fixed cost, no maintenance, nothing, and we are done and got rid of the pumps. We have to express this as a decision making. So let us go back to the basics and construct the decision tree out of it. Again, first element is the square node. What are the alternatives available? Go with pump A, go with pump B, or go with the option C of putting the bentonite seal. I will call it as a seal because I am using nomenclature C for the small pump C that we may have to add. When we go with larger pump, we may deal with some uncertainty here in terms of discharges. There is 90% chance that discharge is 100 GPM, and there is 10% chance that discharge is 120 GPM. When I go with B, again there are two options, 0.9 and 0.1. When there is a bentonite seal, it does not matter, because whatever is the incoming flow, bentonite seal should work for 100 to 120 GPM because I have fully cut off the phreatic lines that are being developed. So there is this particular part remains largely very simple. Let us focus on A. I have not brought into the damage costs because here I do not have any tolerance for water to enter into the system. So if pump B is rendered insufficient, I am installing pump C there. So there is no chance of failure because I cannot afford that, because there would be vehicles, people using that particular subway. So I want to make it 100% reliable. So there is no satisfactory versus unsatisfactory performance. It has to be rendered satisfactory even with augmentation of capacities of pumps installed. When we go with A, the installation cost is 20, maintenance cost is 20, because if discharge is 100 GPM and we are going with A, maintenance cost is discounted by 2 units. That means if discharge is 120 GPM and we go with A would be working at full capacity. So the maintenance costs would be higher, that is 22, but installation costs remain the same, that is 20. So this is my installation costs and this is my maintenance cost, and this is what we mean by discounting, that 22 is now 20 instead of full value. If I go with B, the installation cost is 17 and my maintenance cost is 21. That is given in the question. That is, if we go with B and discharge is on the lower side, 21 is the maintenance cost that I have to pay. If I go with B and discharge happens to be higher, that is, it happens to be actually 120 GPM, what I have to do? I have to install pump B at the cost of 17 as well as install an add-on pump C. That would take another 8 units of money. What about maintenance costs? Unfortunately, I have to now pay full money for maintenance of B, which would run at full capacity because it is only designed for 100, discharge is 120, so it is doing its work at full capacity. Plus, I have to also maintain a smaller pump, which in this case is C, and it has a maintenance cost of 5 units. So the total maintenance cost here comes out to be 26 and installation cost comes out to be 25. And now if I have to calculate the total expected cost, it is simply 0.9 multiplied by 40, 0.1 multiplied by 42. Because this is the probability of this is 0.9, total costs are 20 plus 20, total probability 0.1, total costs are 20 plus 22, and hence 0.1 into 42. When I go with option B, the total cost in first case are 0.9 into 21 plus 17, 38. In second case, 0.1 into 25 plus 26, which is 51. So in this case, if I have to calculate the expected costs given I go with option A, I have to pay 40.2 units. If I go with option B, I have to pay 39.3 units. And if I go with option C, that is bentonite seal, which is a fixed cost product, I have to pay 41 units. So now, amidst all the confusion, I have a clarity that I will go with option B, because if I have to only make a decision on cost benefit analysis, 39.3 is the lowest one among all these three. I'll pay 39.3 units. I'll go with the smaller pump. And if my discharge is indeed 120 GPM, I will augment the capacity by installation of a smaller pump. And even if it looked like, oh, I have to now pay additional maintenance costs at the end of life of that particular project, I am still investing lesser money by going with option B. And this is one good example that how a real world information that comes with so much numbers and uncertainties towards you can be systematically analyzed and we can convey with confidence that based on the cost benefits associated with options, I am going with option B. Even if our common sense would have said, yeah, that we can go with option B because it costs less upfront money, we still need a much broader rationale to also account for the uncertainties associated with that, and that's what this probability inclusion of probability into decision making enables us to do. Now that we are familiar with this concept of decision tree, let us talk about prior analysis versus terminal analysis in decision making. Whatever problems we were looking into, they all broadly fall into this problem of prior analysis. That is, when we came to construct the decision tree, all the information was available to us, like what is the probability of failure, costs associated, and we start constructing our decision tree. And this is why it is called as a prior analysis. If you recall, we also had a word prior when we were talking about Bayesian uh, Bayes theorem, where posteriors and priors were related to each other through likelihood. And this prior analysis borrows the term or name from there only. And this uses initial data and assumptions without updating from new evidence. We also have the equivalent in decision trees, what we call as terminal analysis. In terminal analysis, we update the analysis as and when new information is available. If you recall, when we were looking into Bayesian framework, we looked at a very similar example where we finished all the exercise, determined probability of floods greater than certain magnitude, and then new information became available to us. What we did is that we somehow found a mathematical way to incorporate that particular information systematically into our analysis, updated our prior beliefs, and got a new distribution and used that to determine all the probabilities. And that is what is essentially a terminal analysis. New information incorporated, updated, and a new decision is being made. And whenever these new data and insights are available, here also we use the Bayesian framework to update that particular information, and we will look into some examples that how this comes into picture. But this distinction is important to make, that whenever prior information available to us, we go with prior analysis. As and when new information is available to us, we want to update that probabilities in our decision tree using the Bayesian framework, and that would constitute the terminal analysis. Also, in previous examples, our cost was known to us deterministically. That was, it was given to us that pump A will cost 20 units, pump B will cost 5 units, or whatever number we discussed. But in many cases, that is not the case. Even the cost is the function of magnitude of event under consideration. For example, cost associated with floods, some researchers may assume that the money we have to pay with amount of water exceeding the river banks may be a linear function, that is 5x, 6x, 7x. In some cases, if there is a heavily urbanized industrial town, that costs may increase exponentially as height of water may increase. So the cost function associated with the water depths can take an exponential form. In some cases, it may take some another form depending upon how the environment of that particular hazard changes, and hence that also becomes an important source of uncertainty in our decision making processes. So we will see in few examples that how choice of cost function can significantly alter the final decision even with the same prior information that is available to us. And not only they would impact the magnitudes, they can completely flip the choice of decision that we are going to make, because ultimately it is the cost at which we terminate our analysis. And hence, if our cost function takes a different form, it can result in very different values or magnitudes of total risks associated with a particular event. Hence, it is very crucial to consider all possible functional forms of the cost function. And sometimes once we do analysis for all the options and different cost functions, decision makers also use some weighing, that I consider this linear form to be 10% important, this exponential form to be 80% important, and some other form to be remaining 10% important, and give the weighted consideration to the final decision. Again, the point here is that even if we are dealing with decision trees, we are still dealing with uncertainties at every time step, every decision point. However, this is the systematic approach to take a decision, or reach to a point where some mathematics is backing your decision. That's why decision trees are indispensable despite all that uncertainties and sensitivities involved in the analysis. Now, to reinforce these particular points, I think nothing better than an example, again taken from our textbook. Here is an example that covers a different kind of hazard. In this case, we are going to talk about an earthquake. So, let us look into this lot of information that is available slowly, try to build that mental map or story, and then we will construct decision tree out of it and see how choice of cost function can alter our decisions. So here it's about an earth dam site selection, and we scrutinized an area that we want to construct a dam at in a particular region to store water, and we identified two locations. One is site A and another one is site B, and these are two final sites that we are considering. We did the survey and we found that if we go with site A, the total yields, positive yields, are of order of 22 units. That is gains minus construction and maintenance cost, number comes out to be 22 units. And site B will give us the returns of 20 units. If I stop here, there is no brainer that go with option A because it is giving higher returns, and we have already accounted for all information that was available to come at these particular numbers. So these two numbers are not the matter of discussion here. What is important is when risk comes into picture, how the uncertainties about A and B comes into picture, that is more important for us. Now both of these locations are susceptible to earthquakes. Now we have to account for the earthquake. Then what we did is that we conducted seismic studies of that particular area and calculated that annual mean occurrence rate of earthquake with damaging intensity that can actually cause damage to that particular dam is that at site A, it can have 0.01 or 0.02 as occurrence rate. We are not sure about that. That there is 50% chance that we may have a 100-year return level event or a 50-year return level event at location A, and there are 50% chance of that, because ultimately we are also using some probability distribution functions to derive the return levels, and even those distribution functions, the choice of which will have some uncertainties, and that is why that is also not clear to us. Similarly, when we went to B, these annual mean occurrence rate are estimated to be 0.005 or 0.01, again with equal probabilities. Now you see that A has higher annual mean occurrence rate of damaging earthquakes than B. A was much more beneficial than B. Now with this updated information, confusion has started creeping in, that should I save that 2 units or put my entire infrastructure to at higher risk? And even there is uncertainty here. So now we have to understand how to bring that into picture. Also, we learned that earthquake occurrence may be modeled as Poisson process. So some more information is available to us. We already learned about Poisson distributions when we spoke about discrete distribution, and I strongly encourage you to refer to the notes of that particular distribution, which is often and widely used to in discussions around earthquakes, and sometimes also number of floods that a particular location can have. So very important distribution in risk and resilience world. And it is also assumed that earthquake damages will be repaired after each earthquake and dam will be restored to its original condition. So construction costs again would be repeated. What is asked to us is that let X be the number of earthquakes occurring during the design life of 50 years. We have to determine the expected loss for both sides when loss function is L equal to 5x. So if one earthquake occurs, loss would be 5 units. If 5 earthquake occurs, loss would be 25 units. Both of these sites can have different number of earthquakes occurring. But one thing to note here is that here loss is a linear function of number of earthquakes occurring in a particular location. So we have to essentially make our decision around that. So let us summarize some of the useful data that we encountered in that big text that we read. And after that, it would be easier for us to set up a problem as a decision tree problem. At site A, we have total returns of 22 units. At site B, we have return of 20 units. Number of earthquake per year. At site A, it can be either 0.01 or 0.02. Chance of this happening is 50%. Chance of this happening is 50%. Equivalent information at site B is 0.5 into 0.05 and 0.5 into 0.01. Loss function in both cases is simply 5x. Another piece of information that we would need is expected loss. Expected loss is whatever is the loss function, L of x, and probability distribution of Px, which are how many earthquakes will occur. One earthquake will occur, or 2 or 3 or 4, which itself is a probability. So expected loss would be Lx multiplied by Px, and it would be summed over all possible values of x. That is, we can have 0 earthquakes, and theoretically we can also have infinite earthquakes. So the summation domain would be 0 to infinity. X cannot take a negative value. And we know that this loss function is 5 into x into Px, x equal to 0 to infinity. We know that this 5 can come out because it's a constant. So x equal to 0 to infinity, x Px. What is this x Px? It is expected value of x summed over entire domain of x. So this is 5 into expected value of x. Now, number of earthquakes follow Poisson distribution. When we talk about Poisson distribution and its mean, the parameter itself is the mean over a period of 50 years. So it is simply 5 into 50 into parameter of Poisson distribution, which we will write as nu j. Mean occurrence rate per year over design period 50 years. So the parameter takes the value of mu j multiplied by total time under consideration, which in this case is 50 because dam is designed for 50 years. So expected loss is simply written as 250 multiplied by nu j in this particular case. Now, with this information, we can work on the information about expected loss. For clarity, I will just take this information and paste it here, and whenever needed, we can refer to this particular section. So expected loss, given that we make dam at site A is 250 nu j. Nu j can take two values, each with probability of 0.5. So I can write this as 250 nu j2 into 0.5. At site 1, this value was 250 into 0.01 into 0.5 plus 250 into 0.02 into 0.5, which is equal to $3.75 million. What is net benefit at A now? Net benefit is total gains that we expected minus total loss that we expect now because of earthquake in a given year, and this number comes out to be 18.25 million. If I talk about expected loss for option B, this comes out to be 250 into, again it has two parameters, each with confidence of 50%, plus 250 into 0.01 into 0.50. This comes out to be $1.875 million. And expected net benefit here comes out to be 20 minus 1.875 is equal to 18.125 million. So despite the earthquake and the linear loss function, site A remains the winner because it is giving us more benefit. So I will go with the option A, and even if the expected loss is higher, it is not able to offset the gains I am reaping by putting dam at location A. Hence, choice is clear. Now, with the same framework, we can ask next question, that instead of loss being 5x, what if loss takes the value of 3 raised to power x? How my decision will get altered? Again, I will start putting things together in a same fashion, that I want to calculate expected costs here. Again, expected costs is Cx, Px, x summed over its entire domain of 0 to infinity. Some repetition here, but I think very important, because that's the elegance of expected values. They would keep on repeating themselves and can be easily substituted in our expressions of interest. Now, unfortunately, here we will not end up with a beautiful form of xpx and simply write it as expectation of x. So we have to go to the fundamentals of probability distributions again. Cx is given as 3 raised to power x. What about px? Probability of x follows Poisson distribution. E raised to power minus lambda. Lambda in this case would be 50 times nu j, because 50 is the total design life of that infrastructure. Lambda raised to power x, 50 nu j raised to power x divided by x factorial. Right? If this is correct, we can write this as, now 3 can go inside. This can be 3 into 50 nu j raised to power x, e raised to power minus 50 nu j upon x factorial. This is simply 150 nu j raised to power x upon x factorial into e to the power minus 50 nu j. if I focus on first summation, if I have to expand an exponential function e raised to power y, its expansion also looks like y to the power n upon n factorial, where n goes from 0 to infinity. This has nothing to do with risk or probability. This is simple Eulerian expansion of e to the power x. On any exponential function x can be approximated as sum of x plus x square by 2 factorial and so on. And I can simply write it here. Now, if you look into this closely, we have something like y to the power n upon n factorial sitting here. So, where we can simply say that if I have to simplify it further and get rid of this factorial, this is e raised to power 150 nu j into e raised to power minus 50 nu j. So, these two terms that I have highlighted, they are similar to each other, where y takes the value of 150 nu j and it's an exponential of x. Now again, I emphasize here, we use Poisson distribution, we ended up with this particular form of mathematics. This can be a total surprise, but while working on risk, decision and resilience problem, I would not be worried about the mathematics. I can always borrow that particular tool or trick from mathematicians. But my objective is to come at a decision while ensuring that I cross all the hurdles of that particular mathematics. So I would not be bothered that this takes such an overwhelming form. But here, to put it simply, we are borrowing it from mathematicians and putting it in our broader objective to reach whether dam should be built at site A or at site B, using some of the standard or sometimes some not so standard mathematical functions that are available to us. Here it becomes e raised to power 100 nu j. This is our cost function now. We are done with all, we are away with all factorials and integrations and summations now. So again, we will go back to the same expected loss given A, 50% chance that I have parameter as 0.01 and 50% chance that I have parameter as 0.02. This comes out to be 5.06 million. These are the losses, by the way. For expected loss given B, 50% chance that my parameter is 0.005, or just to make sure that we have this number correct, it was 0.005 from the original question. 0.005 plus 0.5 into e to the power 100 into 0.01. This comes out to be 2.186 million. Now here, decisions are going to diverge. We were saving 2 units while going for A, but now the loss is already offsetting that gains that we are getting by putting our dam at location A by more than the savings that by more than 2 units, because now risk has exceeded that 2 units in comparison to B. So in this case, B becomes our preferable choice. So the moment we change the functional form of our cost function, our decision changed towards B. Now, same discussion can be extended that how can we now determine the expected loss for both sides when loss function takes the form L equal to 5x square, and we can make a similar mathematics around that. I will of course do it because this will also bring the variance into picture, because essentially whenever we talk about expectation of x square, we are talking about second moment, which is closely linked to variance. So for sake of completeness, we will also see that when functions are of x square form, how the losses or cost function would shape up like. So in this case, expected cost of Cx can again be written as summation from x equal to 0 to infinity 5x square px, 5 comes out, x equal to 0 to infinity x square px, which is equal to 5. What is x square px? It is expectation of x square, or what we also call as second moment. If we recall, variance of x is expectation of x square minus expectation of x whole square. So I can simply say that expectation of x square is equal to variance of x plus expectation of x square. It's a Poisson distribution. Variance is same as mean. So variance in this case is 50 nu j, because 50 again is the design life, and mean of course is 50 nu j, and we have to take its square. So this comes out to be 50 nu j plus 2500 nu j square. So my expected costs now comes out to be 250 nu j plus expected cost in this case, it would be multiplied by 5 from outside, by the way. That's why 5 times 50 is 250, and this would be 12500 nu j square, because this has to be multiplied by 5 that we left outside, as a result of which my expected costs come out to be this. Now if I plug these values again, this comes out to be expected loss of A is 250 into 0.01 plus 12500 into 0.01 square into 0.5, because 50% chance we have nu j as 0.01 plus 250 into 0.02 plus 12500 into 0.02 square, again multiplied by 0.5, comes out to be 6.875 million. I can work out a similar number for site B, because again parameters change. I will not do it here, but that risk comes out to be 2.636 million. Again, we were saving 2 units when we were going with A. The total difference in the risks associated from earthquakes is around 4 units. So again, what was no brainer when we were not having information about risk to go with A, now shifts with B with an updated loss function. Now, in these examples, I think we developed a very good understanding that we can incorporate the uncertainties associated with probability of hazard itself. We can incorporate uncertainties about the assumptions as well as hazards when they are brought together. And we can also incorporate uncertainties associated with the choice of cost function. And that gives us a very solid point to conclude our discussions about prior analysis, that whenever given certain information and assumptions, how we can use all of that to make a decision. In our next lecture, we will look into combining some uncertainties in decision tree. That is, what if these probabilities themselves have some uncertainties associated with themselves of realizing, but that we will discuss in the subsequent parts. Thank you.